Yes. Yeah, I think you're the only one here. Well, we can record it. There's 5 people now watching. Okay, so we got 5 people in again. Okay, so we're gonna start back on question 2. Let me just start talking again. I'm sorry for all the technical difficulties, everyone. This is literally my first time doing this. So we're gonna start talking again on question number 2. We're gonna try to get through some more questions on the test. Give me any feedback you want in the chat. I'll probably relabel and recut these videos and everything. So talk to me in the chat, like give me some feedback, give me some positive encouragement, because with me, I want to make this work for you guys really well, because I want this to be like, oh, we do like really great reviews on YouTube and then they're all posted. So keep giving me feedback if you guys want. You don't gotta be like, you're great. I mean, that's all right, but I want like, hey, this is working, or hey, do this. Like, you guys are directing me in this. So with this in mind right here, let's talk again on question 2. With question number 2, our null hypothesis, as we stated, is that the drug is safe. So with this in mind right here, we're going to switch over to, I'm going to share the Word document now. And with the Word document, let's switch over, and hopefully it doesn't get angry at me sharing so much. With the Word document, we have written on here, the null is that the drug is unsafe. The alternative is that the drug is safe. Now, with this in mind right here, just think about it. A type 1 error is a false positive. A false positive means you have evidence when you don't actually have evidence. Evidence of what? Anytime I say evidence, you should think evidence for the alternative, because the alternative is the evidence-based claim. You would believe the drug is unsafe until you get evidence that it's not safe. I mean, you would believe the drug is unsafe until you get evidence that it is safe. You want to like show me that drug is safe before we put it on the market. So with this in mind right here, in a type 1 error in this instance, we would reject the null because we have evidence for the alternative. So think about this. If you're rejecting the null, you're saying, I'm throwing this away. So you throw that away and you say the drug is safe. I have evidence the drug is safe, but you were wrong. So if you have evidence the drug is safe, or you believe you do, you're going to put an unsafe drug market on the you're going to put an unsafe drug on the market in a type 1 error. Now, in a type 2 error, it's a false negative. You don't have evidence for the alternative. So in a type 2 error, you would go in here and say the drug is unsafe. You're going to say, I don't have evidence for the alternative. I don't have evidence. That's a false negative. I don't have evidence. So if you don't have evidence, you're going to say, yeah, I still believe the drug is unsafe because I didn't have evidence elsewise. So in this instance, the drug is actually safe, but you continue to believe it's unsafe. So an unsafe drug a safe drug does not go on the market because the drug is actually safe. You just didn't find that evidence. The truth is the drug is safe. You should have rejected the null. It was a false negative. Negative meaning you didn't have evidence. You should have had evidence for the alternative. Now, the type 1, type 2, and this is very important, are contextual on which one is worse. If you're very sick and you're going to die very soon, then you might not mind so much a type 1 error. Type 1 error is when we say the drug is safe when it's not. Because unfortunately, you might be willing to try something experimental if you're in that situation. So when we view it from someone who's willing to try experimental things at the cost of it not being safe, then they might not mind the type 1 error. When we view it as maybe this is some drug that's for everyone, it's some sort of like mass used in hospitals drug, well, in that instance, a consumer advocacy group would be against the release of this drug if it's unsafe. So they would really, really hate if the drug was truly unsafe and they said it was safe. So if we were to make a type 1 error, we would say, aha, we have evidence the drug is safe, but in truth, the drug is unsafe. And that would be a big problem for them. The type 1, type 2 error, which one is worse, is always contextual on which one, just who you are and which one you think would be worse. We have famous questions like, if the teacher is trying to figure out who cheaters are, the null would be, and let's type this in, the null would be that you're not cheating. The null is not cheating. And the alternative would be cheating. So thinking about this instance right here, if we need to find evidence of cheating, if we have a type 1 error, what does this mean? Did we find evidence? Just think for it for a moment yourself. It means we did find evidence. We found evidence that someone was cheating, but it's a type 1 error. The truth is they were not cheating. So for the person, the student, that's horrible. Maybe the teacher doesn't care. They're going on spring break, they're going on, vacation. They don't care. I'm not saying they don't, but for the example. In a type 2 error, we do not have evidence. We do not have evidence, so we retain the null, and we say they're not cheating. So this means a student gets away with cheating. Now, a student might be like, that's awesome. But other students might be like, that's not great. And the teacher wouldn't be happy. So it depends on who you are for which one is worse. There's not like type 1 is always worse or type 2 is always worse. Let's see here. I can't see my icon at the bottom, so I have to tab switch. And let's go back to the test. How's everyone doing? Throw me some feedback. Like, hey, bro, what's up? You guys will catch up to me in the future in a moment again. We'll go on to question number 3 here. Question number 3. Below is some output for a 2-sample t-test. Assume all the necessary conditions have been met for the t-test to be valid. Now, with this in mind right here, the difference is the actual difference between standing and sitting. It's funny, they don't even tell you what much of this is. I'll read the comments here in a second. Standing and sitting are just 2 means. We have a mean for standing and a mean for sitting. Which one of these was higher, standing or sitting? The answer is standing, because this is a positive difference. As we did before, plug in numbers. 10 minus 9 gives you about 1. So the standard error, as we see in the formula down below, is just, once again, since it's 2 means, the standard error is this last part of the formula right here. That is the standard error right here. So a lot of times you'd have to calculate this by hand, but JUMP calculates the standard error for you. So you can even remember that sometimes if you have to use it in a formula, which we will do here in a second. So let's go back up to question number 3, and I'm way past it. So question number 3 right here. Okay, we have some values missing right here for the 95% confidence interval. We have the test right here, and that might help us out later. Right now, we're wondering about the t-ratio that has been removed. With the t-ratio removed, we are actually going to find the t-ratio by doing the difference standardized. Remember, difference divided by standard error. Where have we seen that before? Let's go down and look at the formula again. Difference divided by standard error is just the way we test 2 means. Difference divided by standard error right here is difference divided by standard error. That's all it is. The difference of the 2 sample means divided by the standard error gives you the test statistic with a certain amount of degrees of freedom. That's just a subscript for degrees of freedom. Difference divided by standard error. So this is very easy right here. This test statistic right here is merely 1.0897 divided by 0.9449. And I tell people, literally just put in a divide line right here and write equals. You can just divide these 2 numbers. And you should get something about 1.1 or something close to that. It's going to be right above 1 because 1.08 divided by 1.94 is a little bit more than 1. This just tells us how many standard errors of the mean we landed. It's just like a z-score. Not just like exactly, but close enough we can understand that it's a standardized test statistic. This curve right here is a t with 43.89 degrees of freedom, which is a lot like a z. So let's go down here and do the tougher problem that a lot of people have problems with. The more difficult problem right here is compute the 95% confidence interval. And to do this right here, and I'll look at all the questions in a second, to do this right here, we can do a little bit of logic in our head. Now, when we test the two means right here, the null would be that there is no difference. If you notice, for the p-value I'm hovering on, we fail to reject the null that there is no difference. So if we say that we don't have evidence that there is a difference, that means that 0 could be the possible difference. And take a look. Automatically, we have eliminated all the confidence intervals that don't contain 0. These do not contain 0 up here, and these do not contain 0 down here, because we are failing to reject that 0 is a possible value, as in we believe 0 could be a possible value. To fail to reject that 0 is a possible value means you still believe 0 is a possible value. That is the null, that there is no difference, and the only two confidence intervals that contain no difference are C and D. This is where many people who took this test got confused on figuring out which one it was it C or D? Now, the center of every confidence interval is the estimate. The best estimate of the difference is from the sample difference, and that is 1.0908 or 1.09 rounding up. So going right here, if you notice, we want to get a difference of 1.09 when we divide these two numbers together. And I believe, I think I might have to pull out my calculator right here. Calculator. So what we're going to do, and I'm off my screen, I got it, good. I don't know if you guys can see the calculator. I'm going to see if it shows up on your guys' screen as I'm doing it. I'm going to find the center of these intervals by taking the upper plus the lower. And now when you take a negative and add it on, so we want to find the whole length of the interval, which is upper minus lower, excuse me. So when you take a negative and subtract a negative, you're actually adding it. That's where I got a little bit confused. Because the whole length of this interval right here is close to 4. So let's go ahead and take this right here, and we are going to add on 0.8146. And now we're going to divide by 2, and that's the margin of error. The answer to this appears to be C, because the length of the interval C, and I don't think you guys can see the calculator, that's a bummer. The length of interval C is about 3.8. You can find the whole length just by adding on the negative. And with this in mind right here, the center of this interval will be the upper minus the margin of error. The upper is 2.99. So take 2.99 and subtract your margin of error, that is 2.90, and you get a center of 1.08, excuse me, 1.08. The other one, answer D, does not have the correct center, because when we add, we take 2.44 and we add to it 0.61. Remember, we're just getting the length of the interval, and that gives us 3.05. Divide that by 2 for the margin of error of the interval, and then when you subtract this right here from 2.44, 2.44 minus the margin of error, you get an answer of 0.91. And 0.91 is not the center, 1.08 is. So just by virtue of what the center is, yeah, sorry about not seeing the calculator. Thanks you guys for telling me, but it's, yeah, the screen share doesn't work on the calculator. So if I can write on this, that would help, but you guys can't see what I'm writing either, I think, because that's an annotate. So that, I think, does it for this question. Let's see if there's more parts to this. Let me see if I think we got question answers. Nope. It'll be posted to YouTube. Cool. So you guys will be able to go back and check this, and I think that's going to be one of the best parts of this. Any questions right now? If you ask questions now in the interim, I will answer them, or students can answer them, which is always great. I love that. They can answer them, or I'll answer them after I complete the next question. So if you have a question, feel free to ask it, and I'll scan the questions after I complete the next question. So feel free to ask any question, and then I will answer it after completing the next question. A life insurance company tracks life expectancy information to assist in determining the cost of life insurance premiums, yada, yada, yada. The life expectancy, the insurance company wants to know that last year, the average life expectancy of its policyholders was 77 years. They know this. Not that they want to know. They know last year that the policyholders were 77 years old. The company will change its premium structure if there is evidence. That sounds like an alternative to me right now. If there is evidence that people who buy their policies are living longer on average than before. That's an alternative right there. So once you hear the word longer or shorter or more or less or different would be a two-sided, then you have heard the alternative hypothesis. So with this in mind, the company randomly samples 100. At this point, you should be writing in the margin right over here, n equals 100. Instantaneously when doing your test, write in the margins, n equals 100. 100 policies they have sampled. The average life expectancy in the sample of 100 was 78.32. In this moment, you should write y bar equals 78.32. And the standard deviation right here, this is S equals 4.2729. That's standard deviation for the mean of variable y. In your calculator, it will be S x bar. So this is just the standard deviation of a sample. The only other thing we did not label here is 77 is mu naught. That is our hypothesized mean. 77 is mu naught. It's our hypothesized mean. Assume the conditions to perform a hypothesis test are met. These conditions would be, this is a one sample t-test, it would be randomization, that these people were randomly selected. 10%, that these people are less than 10% of all policy holders. And it would also be the nearly normal condition. We would meet that because a sample of 100 would be nearly normal given the central limit theorem. So the central limit theorem would suggest that a sample of 100, the distribution of 100 the distribution for the sample mean of 100 samples would be nearly normal. So with this in mind right here, we have to write the null and alternative, and let's do that. Let's write some null and alternative stuff right now. Let's switch over and do some nulls and alternatives. Switch and switch and switch them. I wish there was a quick way to switch. Yeah, let's get seen for like 10 seconds, like looking at that. Okay, so here we are. We're back to our null and alternative screen over here. And we need to put in some mu's for this. Why mu? Because it's the true mean. Always use your symbols. Know your symbols. Mu. And we would start by assuming the age of our policy holders is 77, because that's what we saw last year. And then we would want to show evidence for some alternative. Not that we want to show it, but this is the alternative that we could possibly show evidence for, that the true mean is greater than 77. So let's read this in words. We want to do it in statistical notation, but be able to read it. The null hypothesis states that the true mean life expectancy for our policyholders is equal to 77 years of age. The alternative states that the true mean age for our policyholders is greater than 77 years of age. This is the null and alternative for this question, and this is the way you should write it. Okay, so now let's go back to the future. Let's stop this sharing right here. And go back over to the document. Is this it? Cool. I wish it would let me adjust it on that. When I go to the Word document, it goes right back to it. Here we are. Calculate the appropriate test statistic. And this is where I want to use a little bit of logic with you guys. Because guess what? Your appropriate test statistic is already being displayed for you. Take a look at this. This red line right here, or probably on your test when it's printed not in color, would be a black line. That is the test statistic. Now this almost looks like a normal curve because it's a t with 99 degrees of freedom. If we were to ask you what the t statistic was for this, this is a t curve with 99 degrees of freedom. I might be able to screen share my calculator, and we're probably going to try that out right here. So with this in mind, why are we looking at this when it asks us to calculate the test statistic? Why does this help us? Because we can get an estimate of how far this is away just by thinking about the z's. Now, this is not a z, it is a t, but we can understand it this way and think about it just like, oh, well, that looks to be maybe 1, 2, 3 standard errors of the mean away. it's a pretty decent estimate. If we get an answer for negative on our test statistic, we've done it wrong. If we get an answer like 1, we've gotten it wrong. So it's a kind of a check to make sure you're on the right track. Another check for us also is when we see this up here, if you notice the probability right here, the p-value is 0.0025, which is almost kind of like 0.003, the area outside of 3 standard deviations according to the 68, 95, 99.7 rule. Wait, this all looks like the test statistic should be very close to 3. So now that we've got an estimate of what it should be, let's go ahead and find out exactly what it should be. So here we go. We're going to try sharing the calculator for the first time. Let's see what happens. This is that show. Let's see what happens live. Screen share calculator. This is going to be interesting. Oh, that's kind of cool. It's way big. So I'm going to have both things pulled open here so I can use the calculator and screen share at the same time. So when we do this test, we always do observed minus expected over a standardizing factor. So the first thing I'm going to calculate is the standardizing factor because I'm going to just save that. The standardizing factor is S over the square root of n. S over the square root of n. If you want, scroll down to your formula sheet right now. You can pause the video if you're not watching live. And you can look at the one sample test of a mean. This is one sample test of a mean t-test in your calculator. So I'm going to calculate the standardizing factor, which is just 4.2729 divided by the square root of 100, which is 10. Because that's 4.2729 divided by the square root of 100, and that's 10. Look up the formula on your formula sheet if you want to see what I'm doing. Plug these in. I'm going to copy this right here. And now I'm going to take the observed mean, which is our sample mean, minus our expected mean. Observed minus expected divided by that standardizing factor I just calculated, and boom, 3.08. That is awesome. So what did we think it was? We thought it was close to 3. Remember, and here it's 3.08, and let's look at this again visually in the picture. I'm going to find a quicker way to switch because that would make it awesome for me. So when we look at our results right here, we can see on this visual picture that we did land about 3 standard deviations above. 3 standard deviations above, and our t-score was 3.0892. Now, using the alpha of 0.05, we need to pick the right p-value. The right p-value here is the one that has the greater than sign, just like our alternative. We did greater than 77. It's just like greater than, you can plug that in. This is the alternative. And what are we going to do? We are going to reject the null with an alpha of 0.05. So do these sample data indicate that the insurance company should change its premium because the average life expectancy of its policyholders has increased? Yes, it does, because we have evidence. The probability of our results or results more extreme due to random chance variation, given that the null is true, is about 0.13% or 0.0013. As in, yes, it seems very likely that the true mean of our policyholders has increased from 77 years. We would not see these results or results more extreme given 77 is true. We would see them, but not very often, as in we're not going to see these results very, very often. It's not common to see these results. Once again, I'm going to state this here. If you want to state your null alternative in context of the problem, the easiest way to state things in context of the problem is to just go back to your null alternative. And let's go to where we've written them. So the null states, so we reject that the true mean of our policy, the true mean age of our policyholders is equal to 77. We have evidence that the true mean age of our policyholders is greater than 77. This is all you have to do to state it in context. To state in context, just go back to your null alternative. I reject that the true mean age of policyholder is equal to 77. I have evidence that the true mean age of policyholder is greater than 77. That's, oh good, I thought we crashed again. I was really freaking out. Sorry, you heard me pause there, but I thought we crashed. We didn't. So that is excellent for that problem, and we're still going strong because it crashed last time about 27 minutes, and I was about to freak out. That's that. Okay. So let's go back in here to our stuff right here. Okay. I like this stuff. UT decides to analyze the relationship between the Greek. Well, let's see. Remember, if you have any questions at this point, ask me a question about anything on this test. I'll answer it after this question. Any questions, go ahead and ask. So any questions, go ahead and ask. A UT student decides to analyze the relationship between Greek life and family economic level. The jump output on the next page shows his analysis of the data, which was taken from a survey group given to spring 2014 Statute 1 students. The Greek life variable indicates whether or not the student was in a sorority or fraternity. Family income level has 3 classifications. Assume that all necessary conditions for doing a hypothesis test are met. So I think what we're analyzing here is categorical data, which is going to give us a chi-square. So going down here, let's just take a look, and we are. This is categorical data. It's doing a chi-square. So the conditions for this, you just start it out, you're like, boom, randomly selected. We got it. 10%, less than 10% of all students are sampled. Next condition, since it's categorical, is that it is count data. And this is count data because if you notice in here, we have a count of how many people were lower class and not in Greek life. How many people were middle class and not in Greek life. That's just a count on those people right there. The final condition is the expected cell count condition. And we might actually be able to check this one right now. The reason we can check it is because we can check the smallest expected cell count, and if it's bigger than 5, they all pass. And I know we have this one blanked out right here, but check this out. The smallest expected cell count would be obtained from taking 110, timesing it by 335, and dividing by 898. That will obtain you the value of 41.03, which is the smallest row and the smallest column times together, and then we divide by the total. So right here, since we pass on the smallest expected cell, then we pass on all of them. If you notice, all these other ones here are bigger, like 222 and 271, which this is actually the biggest because it has the biggest column total and the biggest row total. So we pass on all the expected cells. That is excellent. So we pass all the conditions here. Smallest expected cell count passes, they all pass. Let's go back up and look at the problem right here. Stop it. State the null and alternative hypothesis to explore a possible association between the two variables. Now, this is the only one where we allow you to write it. On all the other ones, we want you to use statistical notation. On the chi-squared, it is all right to write it because it's kind of a nuisance to not. So I'm going to decrease the size of this all because I have to write a little bit more. So the null hypothesis states that there is no relationship between blank and blank. The alternative, I guess we're writing it. The alternative hypothesis states there is a relationship between blank and blank. So in this example right here, the null would state there is no relationship between Greek life and your family's economic level. The alternative hypothesis states there is a relationship between Greek life and your family's economic level. Remember, we're starting out assuming nothing. Well, I don't know, there's nothing going on between those two variables. And then we want to show evidence of a relationship. So we'll have to see how that goes with this test. There's your null and your alternative. Okay, let's start sharing back here again. I need a switchboard person. Maybe we could hire somebody to switchboard. Like, I'll be like, okay, switching cameras, and they'll just like switch over. Okay, so going right here, use the contingency table in the next page to solve for the 3 missing values. And I highly suggest using your calculator on this. Everyone's calculator should have stat chi-squared test. So that's easy enough to find. But right here, so maybe have my Hangout, have this open on one page and have the other one open on the other page. Like have this open so you can see, because I'm about to go to the calculator. So take a good look at this, have it open and try to solve for these values. So I'm about to share the calculator. Put the calculator open. Okay, so with this right here, To calculate a missing count, well, all the counts have to add up to the row total or the column total. So if you'll notice, the column upper class has 433. If we subtract 208, we obtain the total of 225 people. And you can double check that by adding 93, 245, and 225 to see if they add to 563. Now, the more complicated ones that people have problems with are the expected, and let's go to that. The expected is row total times column total over grand total. The row total for the no lower class is 563. Times that by the column total of 110. And divide by the grand total of 898. That is how we obtain an expected count. Also, the expected counts should add up to the total in the row or the column. 69 plus 41 equals 110. Just take a look at that. 69 plus 41, and I'm rounding those numbers, equals 110. You know you've done it correctly if your expected cell counts add up to, I want to show you guys this. 69 is what we got for the expected. I want to make sure everyone sees this. Make sure everyone has their notes open and they see this, because this is something really great. Sorry for when I have to switch it. Why can I not see like that? There it is. 69 is what we solved for in this blank right here. Plus 41 equals 110. Do you see that? I can't get the response yet. But 41 is what I'm rounding this to, and I rounded this to 69. Don't round it on the test. But if you add up the decimals, they do equal up to 110. 69 plus 222 plus 271 would equal 563. That's how it all adds up. So let's do the last value here, the chi-squared. We are going to have to take the observed, which is 110, minus the expected, and do quantity squared, and then divide by the expected. So it's going to be 110 minus 132.433, square that quantity, and then divide by 132.433. Observed minus expected, quantity squared over expected. So let's do this right here. If I do this again, I will know better how to switch between stuff. Like I said, this is just my first time doing this, and so we're ironing it out a little bit. So observed was 110 minus expected, and then we take quantity squared. We just squared it right there. It keeps the same number in. Divide by the expected, and 3.799. Now, with this 3.799, I think I've done everything correctly. I think to make a mistake while doing this for you guys. This 3.799 is the value that tells us how odd the individual cell is. To get the Pearson chi-squared, which is deleted here, we need to add up all of the cell chi-squareds. So you need to add up all these, not the ones that are highlighted there. 8.3, 2.2, 7.9, 14, our 3.8 in here, and our 13.36. That's how you get the Pearson chi-squared. Lastly, this is a 2x3 matrix. Since it's a 2x3 matrix, that means if we shade in our L right here and delete stuff off, it turns into a 1x2. 2x3 is a 1x2. Just reduce each number by 1. 1x2 only has 2 cells. 2x3, 1x2. I'm taking 2 turning into 1 and 3 turning into 2. So if I had a 9x9, that would be 8x8. If I have a 5x5, it's a 4x4. If I have a 2x10, it's a 1x9. I'm just reducing each number by 1 to find the degrees of freedom. Let's keep going down. So we've answered all these questions. Use the output on the previous page, and one of the values you calculate to calculate the chi-squared test statistic. Just add up all the cell chi-squareds, all those cell chi-squareds. Let's see that again. All the cell chi-squareds, where it says cell chi-squareds, all of these add up to the Pearson chi-squared test statistic. State your conclusion in context of the problem. I love this, because what do we do right here? This is the best part of it ever. Look at the p-value. Here's your p-value, because the Pearson has your p-value. So we will reject the null. But what does that mean? All we have to do is go back. This is the best part ever when it says in context of the problem. Context of the problem, we can do that all day long. If I can break up word. So context of the problem, I reject that there is no relationship between family economic level and being in Greek life, I show evidence that there is a relationship between family economic level and being in Greek life. Just, I reject this, I show evidence of this. And make sure to say the full thing. Write it out fully. Just that's all you have to do to give in context of the problem. Just, I reject, and then state what your null was. But remember when it says, like, don't leave the statistical wording when it says in context of the problem. Make sure you're actually saying it like a sentence. This one's really easy to say like a sentence. I want to make that clear. In context of the problem means pretend you're talking to someone about this who has no idea about statistics. Like, oh, I reject that there is no relationship between this and this. I show that there is evidence. I've shown there is evidence of a relationship. So pretend you are talking to someone who doesn't know statistics when it says in context of the problem. We don't want to hear I reject mu equals this, because you're just literally then you might get some points to some people. It's better than a no answer. Just say it like a sentence when you do it that way. Okay, use the mosaic plot to help you describe the nature of the association. This is a great question. I love it because you have to take a look at it. So Greek life, yes, tends to have more people in upper class, and that makes sense. I think we all know it takes money to be in the Greek life because you have to pay dues. I mean, there are people from all different economic levels who are in all, Greek life or not Greek life. Obviously, there's upper class who's not in Greek life, and there's people who, these are self-described people saying that they come from lower class who are in Greek life. But we generally see people with money to be in Greek class more, to be in Greek more. And this is real data, so that's what we generally see. Okay, how are we doing, everybody? How are we doing? Let's get some feedback. Just how are people doing? Any questions? Remember, this is your time to ask questions. I'll answer them in the interim. We're doing great. I think we can get through this all by 7, and then I'll just talk to you guys, and we'll try to improve this. My first attempt at this, I've said that about 1 billion times now. How are we doing? It's going to take you guys a while to get back to me now. We'll take a 1-minute breather, let you guys catch up. So fast forward the video now if you want. Maybe I can even edit these. It'll be interesting. So I might try to, if I can edit these videos on YouTube from the live broadcast, which I know groups like the Young Turks do this. So Young Turks, great web show if you guys have never seen it. Awesome. Thank you, Ashlyn. I just saw Ashlyn said doing it. I think we had 3 people in here last time I looked. 3. Nice. So there you go. Oh wait, I tried to make you a moderator, Ashlyn. I tried. It doesn't like it. It says the specific user does not exist. Interesting stuff. Good to hear from you guys, Darby and Ashlyn. And we got one more person here. Maybe I have Leroy or John Smith. Okay, so let's go on to the next question right here. Okay, in December 2011, Consumer Reports published a study about seafood. They purchased 190 pieces of seafood and randomly selected food stores and restaurants in 3 states and genetically compared the pieces to standard gene fragments that identified the species. Laboratory results indicated that 21.1% of these packages of seafood were mislabeled by store or restaurant employees. Now, you got to think what they're giving you in this problem. They're giving you a sample size right here. I believe I am showing the same. They're giving you a sample size of 190, and they're giving you a p-hat. There is not an x in this relationship right here. We can obtain x by finding out from this, and I'm wondering if the x is going to be a whole number, which I hope it is. 190 times 0.221 is 42. It's so close. It's 41.999. So if you were to put this in your calculator, you can solve for x. X is basically 42, and it's going to be such little decimal differences. I like it when we do it exactly. What is 42% of 90? 190. 42 divided by 190, it's 22.10526%. So the x for this problem is 42, basically. If you want to, there's an x and there's an n, and they give you p-hat, the sample proportion. Okay, so the conditions right here, nice and easy. Random, 10%, success, failure. And actually, by calculating the number of sample successes here, I actually just checked the success failure condition. The success failure condition says that you must find n p hat and n q hat. So n is 190 and p hat is 0.221. So that's 42. Q hat, so n is 190 again, and q hat is 77.9. So I believe that's correct. If I make a mistake, someone will be like, no, Brad, you made a mistake, and I'll find out a minute later. That is 148. And that is correct because 148 and 42 add up to 190. N hat, NP hat plus NQ hat will equal up to N. Because all you're getting is the number of sample successes and the number of sample failures. That's all we have right here. So let's see right here, how many of the seafood packages in the sample were mislabeled? Oh, this is so easy, guys. I mean, that's why it's a 1-point question. It's a 1-point question because it is easy. Using your NP hat and Q hat condition, you will have found out 42 were mislabeled. So we got that right there. And that is a nice and easy one. Compute the standard error. Now, the standard error is the formula, and let's scroll down to it, for a confidence interval. The standard error for the confidence interval is going to be right here. This bottom portion is the standard, excuse me, very sorry, I said confidence interval. The standard error for the confidence interval is p hat, q hat over n square root. And things are called a standard error because they come from an estimate. Down here, p naught and q naught are assumed to be true, so this is a standard deviation. So we are doing the standard error of the confidence interval. So we need to do p hat times q hat over n square root. So the standard error, and let's switch over to the calculator right here. Go ahead and have written down right now 0.221 and 0.779. That's your p hat and q hat in decimal format. 0.221 and 0.779. They're complements of each other, they add up to 100%. So the standard error, let's switch over here to our calculator. Literally had to itch my nose in that second. So let's go ahead and do p hat times q hat over n square root. So p hat is 0.221 times q hat 0.779. P hat times q hat over n, which is 190, and then square root. So there it is, it's 0.03, 0.0301, 0.0301. And so let's go back. I just saw myself itch my nose. Isn't that annoying? Okay, we're going back right now. Myself up. And don't do anything embarrassing on camera like itch your nose or play with your hair. I would never play with my hair on camera. Online students get them up there. So going down right here, construct a 95% confidence interval. And think about this. We've calculated the standard error. So for the standard error, we already have that. The 95% confidence interval is going to be p hat, which is 0.221 plus or minus z star, which is 1.96, and then times the standard error we just found of 0.0301. Now, think about this even further. I'm not saying do this on the test, but round your standard error to 0.03. Now round your z to 2. Now, I'm not saying do this on the test. Don't do that on the test. Don't round things on the test just like that. But for the context of this, if z is 2 and this is 0.03, what is the margin of error? If z is 2 and this is 0.03, then the margin of error is 0.06. And I'm saying this is just a way. Thanks, Ashlyn. You're totally right. I'm putting my hair right now. 0.06 would be the margin of error. So 0.06 is the margin of error. And with this in mind right here, we know that p hat is basically 22%. So the margin of error is 6%. So an estimate of this confidence interval, just by doing it in your head, estimating, rounding this to 22%, 22% plus or minus 6%. Remember, this is very close to 2. This is very close to 0.03. 2 times 0.03 is 6%. This is very close to 22%. 22 plus or minus 6%. So all that is going to be 16% to 28%. And that's a good estimate of our interval. You can check the key for the exact answers. I'm just kind of stating it that way because it's easier for me to state. The key has the exact answers, and it should be close to 16 to 28%. And I think we give interpret your conceptual in part in context of the problem. I'm 95% confident that the true proportion of mislabeled packages, and let's go over to our Word document now. So under our Word document, do not itch nose. Let's write our confidence interval interpretation. I am blank % confident that the, and this is the big blank, is contained in the interval. Let's interpret this right here. I am 95% confident that the true proportion of mislabeled fish packages is contained in the interval 16 to 28%. And please calculate that exactly. Like someone just said, to be fair, Brian does not want to round the exam. Yes, I would hate it. We're like, well, Brian just rounds all the time. I do it to kind of get an estimate in my head of what it should be. That way I know if I do it on the calculator and it comes out all crazy, either I've done it wrong in my head or on the calculator. So just kind of get an estimate. You don't have to do things like that, but it helps me know where I'm at and if I punch something in wrong. Because believe me, if you forget to square root or you forget to divide, all of a sudden things turn out crazy on your calculator. So let's go back. Thank you, Ashley. So, okay, let's go over here. I hit screen share, but it doesn't like the screen share. So next time I'll never put in an end time for these reviews because that's something weird happened with it. Where is my test? Here we are. So we're back to screen sharing the test right now. Interpreting the context of the problem. That's it? Well, we could maybe even bring up a little more to this problem. The company wants to know if there's evidence that less than 30% of their fish packages have problems. Do they have evidence that less than 30% of their fish packets have problems? And the answer would be yes. Well, I mean, that's still a lot to say we have evidence that less than 30%. You know, some consumer advocacy agent claims that we want to know if 30%, if less than 30%. And since 30% is not in the interval that we created an interval that says about 16 to 28%. So we're saying I'm 95% confident the true proportion of mislabeled fish packages is contained in the interval 16 to 28%. That means 30% is a value we could reject. And we would reject it at the 0.05 level. Why the 0.05 level? It goes back to one of your homework questions, because if you create a 95% confidence interval, any value you test would either be failed to rejected or rejected by virtue of being in the interval, fail to reject, or out of the interval, reject on a two-tailed test at 0.05 alpha. 0.05 alpha for a two-tailed test is like a 95% confidence interval. So if I wanted to say, what if I tested the value of 24%? Would 24% be rejected or failed to reject for our interval of 16 to 28%? And 24% would be failed to reject because it's in the interval. We could not reject it at the 0.05 level. Okay, it's time for questions. Write your questions if you got them. If you don't write them. But if you got questions, go ahead and write them. Here we go. An insurance company checks policy records of 582 accidents in the state of Tennessee. Selected at random, and notes that teenagers were at the wheel in 91 of them. So this is a teenager was at the wheel or a teenager was not at the wheel. That's how they're collecting the data. Automatically right here we should think categorical data. So the teenager is at the wheel or they are not at the wheel. The company sets insurance premium for teenagers based on percentage of accidents involving teenagers, among other factors. The company executives decide to have higher premiums in the state and called for tighter restrictions, claiming in at least 1 of every 6 accidents, a teenager is behind the wheel. Is this data consistent with their claim? So with this in mind right here, we want to see if there's evidence that in at least 1 out of every 6 accidents, a teenager is at the wheel. 1/6 is the decimal, and I need to switch back to my word right here. 1/6, if you figure it out on the calculator, is the decimal 1.66666666. That is what 1/6 is in mathematical calculation. So let's go over here and write our trusty null and alternative. Null states that, and is it the true mean or the true proportion? The true proportion of accidents where teenagers are at the wheel is equal to 1/6. The alternative states that the true proportion of accidents where teenagers are at the wheel is greater than 1/6. So remember, we have to state this in statistical notation. Yay! Thanks, Camille. I'm glad you're liking it. So with this right here, we have the null and we have the alternative. So let's check this out. State the null and alternative. Remember, you want to read it like a sentence. If you can read your null alternative like a sentence, you're doing well. The null states the true proportion of accidents where teenagers are at the wheel is equal to 1/6, and that's just the fraction, the decimal of 1/6. The null states, oh no, the true proportion of accidents where teenagers are at the wheel, because all I had was the alternative states greater than 0.166. The alternative states that the true proportion of accidents where teenagers are at the wheel is greater than 1/6. Now we have our null and we have our alternatives. I'll answer the questions here in a moment at the end of this question. So let's go ahead and go back to sharing right here and try this up for some. Switching sharing, switching sharing. Back over to our test. We've written our null and our alternative. Compute the appropriate test statistic. Now we need to make sure we pick the right test for this. This is proportions and there's one proportion. So this is a one proportion Z test. One proportion Z test, as I highlight the wrong one. One proportion Z test. You can do it on the calculator like that, and you need to isolate your values. When we were doing this right here, we had a sample size. That is how many accidents we looked at. We can get a p-hat, which is the sample proportion of accidents where teenagers are at the wheel. Our p-naught is our hypothesized proportion, which is 1/6. Q-naught is just the complement. So this is the sample proportion of accidents where teenagers are at the wheel as found by x over n. X being the number of accidents, and x being the number of accidents where teenagers are at the wheel, and n being the total number of accidents. Let's go ahead and calculate that, and I'm going to do it as an off-screen calculation. This is an off-screen calculation right here. Sorry, everybody. You'll see the numbers on the screen. So the calculation, my calculator will not come up. There it is. The calculation is merely there were 91 accidents where teenagers were out of the wheel out of 582, which is 15.6. Now, instantaneously, I can think of where I've landed on my distribution. I'm going to go back to another distribution and show you something. According to the null, 16% is at the center of this distribution. Now, I want you to ignore these numbers at the bottom of this, so I'm not even going to show them, if I can. So let's not even show these numbers at the bottom. 16%, 0.666 would be at the center. 16.666666 is at the center. We landed at 15. I don't know where 15 is at, but I know it's lower than 16. So the p-value for this is going to be very big because we are doing a right-tailed test. Now I'm showing you just a distribution right here. This is not the applicable distribution to this question. We landed over here below the null. The null is at the center. So let's go ahead and do this right here and do this actual test. So we need to take, and I'll bring up the calculator for this so everyone can see. Da-da-da, calculator time. Okay, calculator time. This is my sample proportion I just calculated. So then I take observed, which is sample proportion, minus expected, which is null proportion. Go back to your formula if you need to check. Observed minus expected. So I observed the sample proportion, and I expected this null proportion. And here's what we get. As we said, the test statistic, which is a z here, will be negative. Next, we need to standardize this. I've copied it. So let's go ahead and do this. We need to take P naught, that is P naught, remember P naught is our 1/6, times Q naught, obtained, they both add up to 1, I'm hitting a wrong number there. P naught times Q naught, the two of those together add up to 1, divided by n, which is our sample size, 582, and then square root. So with this in mind right here, I'm going to take this, and I cheated because I just saw negative, let's just do 10309. Good. That was our difference, if I have it correct. And now I'm dividing it by the standard error of the difference. That was our difference up top. And now I'm dividing it by the standard deviation of P naught. All I'm doing is standardizing this difference right here. This will obtain me the test statistic. The test statistic is negative 0.667. So with this in mind right here, negative 0.667 is below. At this point, when you have this, I would highly, highly, highly suggest going over, and let me try, can I show a new screen right here? Let's see this. So let's go over to David M. Lane applet. Now you won't have this on the test, I know that. I know you guys will not have David M. Lane applet. So let me show you guys David M. Lane applet right here. Why am I showing you this when you don't have it on the test? Because on the test, you can just draw it out. You don't need to be exact in your drawing, just draw it out. Get close to it. So let's view it right here. Because if the test statistic is negative 0.6667, we can just plug it in right here, and we're shading to the right. This is where people maybe get a little bit confused. It was a greater than alternative. So we're shading to the right. And what we know from the empirical rule is that 50% is above 0, and 34%, because 68 in the middle, 34% between here and here, is between negative 1 and 0. So I haven't even looked yet, but I know this p-value has to be between 50 and 84%, and it's probably about 78. And the p-value is 74, 74.77. This is where you can estimate it. You can draw this on your test and get an estimate of the p-value. It'll help you if you ever have to look at any applet stuff on the test, which who knows if there will be or not. Now I'm wondering if when I switch, it switches back to the test. Hopefully I'll be seeing that in a second here. Let's scroll down. And this is the best part of this, because based on what we did here on the David M. Lane applet, I literally just created this. Was I off in creating my test statistic? Because you see here, and this looks to be the right one, I got a slightly different value. And you know what I think it is? Somebody, I want you guys to check for me the exact, what is the exact p-value for the right-tailed test on this? Because I think whoever did this when they created this, they, which it seems like they did it pretty right, they didn't carry out as many decimals as I did, or when I copy-pasted. Can someone get me the exact p-value on the TI calculator for this? So this can be found under one prop z-test. One prop z-test on the TI calculator. Go over and try that. One prop z-test. I want to see what you guys get as an exact p-value. Go ahead and find me that. Let's see if anyone gets it. I just want to make sure I did everything properly, because I think I did. Doing things live, my value is not that different than theirs. But what is the exact p-value and the exact test statistic? Not bring my TI calculator. Whoa! Oh, it's changing. We'll see if anyone answers. The test is showing, so I might have made a small, tiny error. I think everything I did is correct. It's just decimal differences. Also, did I copy paste this in with all these decimals? A lot of times people aren't as exact as I am. I carry out all of these decimals in my calculations, and I'm guessing that they didn't when they made this. Just, Brian being really, really exact. And yeah, so let's assume that is correct because it's only decimal differences. Whoever created this picture probably just didn't carry all the decimals that I did. Oh wow, we're near the end. This is the end of the test. Are there any questions? I don't know if anyone calculated it. We'll see. Maybe I'll check this when I go home, put an addendum on here. 4 people watching, yeah! Darby asked, this doesn't have to do with the test exactly, but do we have to do the Reaver test for test 1 and test 2 on Style Lab? No, I wouldn't do the test 1 or test 2 review. Just the Megatron assignments. Those were for test 1 and test 2, and I probably should close them. I don't know if they're open now. It's my mistake if they're open, but I probably should close them. Let's see these last few questions right here. Ask questions if you got them now. When doing a t-test for the difference between 2 population means, the formula for degrees of freedom is rather complex, and we typically use technology to help us calculate this. That is very, very correct. Let's type in here degrees of freedom 2 sample t-test. We can go over to images and we can see this. The formula is something like this right here. It's ridiculous. We would use it would be calculated that way. A type 2 error is always the most serious error with regards to hypothesis testing. So not true. So not true. And it's not a type 1. It just depends on the context. If you're doing medical research like you were before, you might, some people might say we should have more drugs on the market even if they're not safe. Some people might say, no. Don't put drugs on the market unless it's proven they are safe. That about made a mistake there. But it's just the philosophy of, would you rather say there's evidence when there isn't, or rather fail to find evidence when there is? Saying there's evidence when there is not is a type 1 error. Failing to find evidence when there is a type 2 error, because false negative, you did not find evidence. During the business analytics presentation from your instructor, you heard a story about Target knowing that a teenager was pregnant before the girl's father knew she was pregnant. Now, let's see here. I think a great video for this, Colbert Report, Surrender to a Buyer Power. If you guys haven't seen this, I'm going to put this in the chat. Go check out Colbert Report, Surrender to a Buyer Power. I have no idea what the business analytics question will be for this test, or if there will be one. Did seriously just change that to a smiley face? I can't put links in there. Google Colbert Report, Surrender to a Buyer Power. So check that out if you want. Some of our presentation is based off of that. We talk also about Moneyball and how it changed the name of the game in baseball. Kind of some key points to drop right there. A regression analysis cannot prove a cause and effect relationship between 2 quantitative variables, yet a chi-squared test of independence can prove a cause and effect relationship between 2 categorical variables. I hate to tell you this, but this whole class, statistics, proves nothing. Nothing! Yes and no. Statistics is about showing evidence and even more evidence. Evidence is denoted by the p-value. So when we have a lot of evidence, it's due to a very small p-value. And some people would say that a true experiment, which we haven't talked about in this class, a true experiment would show evidence of a cause and effect relationship. We haven't done any experiments here. We didn't design an experiment here. We didn't use placebos, and we didn't use, I can't think of the word, control groups. So we didn't do that. So we can't say, awesome. Thanks, Ashley. So it is awesome, I agree too. With this right here, we're on to the next one. Large chi-squared test statistics are more likely to lead to statistically significant results. This is excellent because when we look at this right here, let's go on, let's see, chi-squared, chi-squared. So I love this Matt Bogner guy. He's done a great job on these apps. We put in a chi-squared like we're doing a chi-squared with 3 degrees of freedom. And if you notice, if I put in a value of 1, that's a big p-value. 2, 3, 4. You see how the p-value is getting smaller. The p-value is getting smaller and smaller and smaller as the chi-squared gets bigger. because even when we notice our chi-squared test, it even says to the right, probability greater. Let's scroll back up to our chi-squared test. Right here, it says probability greater than chi-squared. As in, here's your chi-squared test statistic, this blue line. Now the probability greater than that, so it's shading to the right. The chi-squared is a right-tailed test. So let's see what the question asks again, because we notice as chi-squared gets bigger, p-value gets smaller, and I think that's what it says. So, scroll down to here. Larger chi-squared test statistics are more likely to lead to statistically significant results. Larger chi-squared test statistics lead to smaller p-values. Smaller p-values are more statistically significant. So, very, very true. For a given confidence level, increasing the sample size will decrease the margin of error. Scroll down to your formula sheet here and plug in a large number. Now, if you notice, you're dividing. So when we divide here, we are making this number smaller, as in, just pretend up top is 1. 1 divided by 1, and let's just pretend it's not square rooted, that's just whatever. 1 divided by 1 is going to give you 1. But now when we do 1 divided by 100, this gets smaller, it turns into a 100, and then you square root it. But it's still smaller. So when n gets bigger, this gets smaller. This is part of the margin of error. This whole over here, this over here is the margin of error too, everything after the plus or minus. So let's see another margin of error. This is a margin of error right here, whole plus or minus. And as you increase sample size, you're dividing by bigger and bigger numbers. Dividing by bigger and bigger numbers makes the margin of error smaller. So we can see that right here. As n goes from 16, this would go to 4 then. If it's 100, it would go to 10. Just makes this smaller, which makes the margin of error smaller, and I think that's what it said. Let's take a look. For a given confidence level, increasing the sample size will decrease the margin of error. Very, very true. I don't know if anyone did. Did you, Ashlyn? Did you check it? It should be right. I think it was right. I don't have my. I left my TI calculator at home. I'll have to go and check that later on. But that ends the review. If you guys have any questions, maybe we'll try this again. And so I might do the exact same review and go through the questions by answering this on YouTube. So we could try round 2 of doing this, and me explain it again. I mean, literally, I'll just be doing the same problems. Or maybe we'll try to do a review where I take your guys' questions. Like maybe people could submit questions on Study Room, and I could answer the questions one by one. Because what I learned from this is that live feedback is not going to work so well on this with the delay. We'll go back to you and me. So live feedback is not going to work so well on this. Hey, what's up, guys? I'll go back here. What's up? See, I got it broadcasting there so we could have people in the class. I think it's gonna be fun if I start doing live broadcasts like this and put them on the YouTube channel. Yeah, is that what I got, Ashlyn? 7.4, I think it was. So I think you got the same one I got. It seems like it. So. So any other questions? What's going on, everybody? Who's got questions? I got answers. People have been texting me like crazy. Just a few random texts in here. Andy said, never mind. What questions do people have? I'm just texting right now. I'm taking a short break. So people at the end of the day, I'm just texting. Any questions? Yeah, exactly. That's why I didn't super announce this. People are like, I didn't know this was going on. It's because I wanted to know how this would go, and maybe Monday night I'll do a live, because I'll do the thing Sunday. So maybe I'll do a review Monday night, the night before the test, and I'll do one of these. So we have to see how it goes. So if anyone has any other questions, we might only have a few people viewing right now. I am broadcasting from our classroom, the one that when people attend, we are going from room 203. So room 203. Nice classroom. Nobody's here. Nobody's here. that's got it. I'll probably end the broadcast soon. I'm very happy that we had some people viewing. I know we got the kinks out by working this. We just like banged them all out. We just kind of molded it into something nice and new. So this will be interesting, and people seem to like it. So that's all I can say. Any other questions? I'll let you guys ask questions now if you want, or else I'll end it. My plan now is for a Monday night, so we could do like a Monday night. Submit your questions on Study Room or via email or anywhere, and then just carry your pigeon. I don't know, Morse code me them, and then I will answer them Monday night. Like, what people want me to do? And yeah, awesome. I'll stop the broadcast. You guys know how to get a hold of me. bstevens@utk.edu. Good seeing everyone. Good seeing. I think we had Camille come in here. Ashton came in here. We had Darby come in here. Who else do we have? This is my thanks, everyone. Leroy, thanks for coming in. John Smith. Thank you to the 9 people we lost. We lost so many people. We had people watching, and then we lost them. So thank you to everyone who watched. Sorry it crashed. And it seems like it started working pretty well. Good deal. Goodbye, everybody.